Okay, good morning. We will start now our last section. The last one is a big pleasure to introduce our first speaker of today, Alexander Suzuki. Alexander Suzuki from the University of Coimbra, and he will talk about some Marcos inequalities related with double polyal sequence in its extension for Toeplitz matrix. Thank you, Alexander.
So I'll talk about some recent results that I obtained working together with Kenner, and these results are extensions of some theorems of Markov. So I'm going to talk first about what Markov did back in the 19th century. So he started with a sequence of real numbers, and from that sequence he constructed the Hankel matrix, which has that form. And from that Hankel matrix, we can obtain orthogonal polynomials on the real line. If we have a result that says that if the Hankel matrix, this Hankel matrix is positive definite, if and only if there is a sequence of orthogonal polynomials which can be written in terms of those elements of that sequence. And if you also impose the condition that the matrix obtained by this one, by deleting the first column and the last row, is positive definite, then all the zeros of this polynomial will be positive. So these results are related to what's called the Stieltjes moment problem. And next, what Markov did was take one of the elements of that sequence and perturb a little, and with that he proved that the determinant of that Hankel matrix and also the zeros of those orthogonal polynomials, they have a monotonicity property depending on how you perturb that element. Just some historical comment here is that the article where this was published was printed, was published and printed in Russian, and was sold for around 15 cents, the equivalent of 15 cents of the United States dollar at the time. But this remained not, these results were not very known until Shohat translated them to English 46 years later, in 1940. And then it started to appear in some books. So for our case, now instead of starting with a sequence of real numbers, we start with a double sequence of complex numbers, and from that and the sequence must have this property, and from that we construct a tuplets matrix that has this form. And from that matrix, if that matrix is positive definite, we can also obtain orthogonal polynomials, but now they are orthogonal polynomials on the unit circle. We can also write them in terms of the elements of the sequence. Okay, so some other things that we need to know first. We can, from those orthogonal polynomials on the unit circle and some parameter of parorthogonality with modulus 1, we can define the parorthogonal polynomials like this. And we can also define the kernel, the Christopher-Darboux kernels, which is represented by this sum. And one interesting result here is that if you have a zero of the parorthogonal polynomial, then the zeros of this parorthogonal polynomial will be, of course, the zero that we took, and also the zeros of this kernel. And these zeros are simple and lie on S1. Okay, so other thing that we need to know is what is a two-sided polyfrequency sequence. We say that a double sequence is a two-sided polyfrequency sequence if the infinite tuplets matrix that we construct from that sequence is totally positive. And that means that the minors of all orders are positive. Okay, so with those things in mind, we can start for results. Again, we take one of the elements of that sequence and we perturb just a little so we can put a dependence of some parameter t. So the first results that we obtained were for determinants. Well, if we start from a two-sided polyfrequency sequence, then those tuplet determinants will have a monotonicity property depending on how you will perturb the element of that element of the sequence. And if instead of starting with a two-sided polyfrequency sequence, we assume that we start with some sequence and we assume that that kernel is a Hurwitz polynomial, and that means that that polynomial, all the zeros of that polynomial have negative real part. Then we will also have the monotonicity of that tuplets matrix. Okay, so now the results on zeros. Here, this result is what we try to do here is to see where is the dependence of the monotonicity, on what that depends on. So that depends essentially of two things. First, how you perturb that element of the sequence, and also depends on some function bk, which can be expressed by one of these two formulas. So this is the case for when you have a pair of conjugate zeros, and we can also have the similar result for the case when you have a fixed zero. It will also depend on how you you perturb that element of the sequence, also some function decay, but of course this will have a different representation. So these expressions for the functions decay might seem a little complicated, but they are nothing more than the coefficients of some Lohan polynomials. For the case of conjugate zeros, they are the coefficients of this first Lohan polynomial, and for the case of fixed zero, they are the coefficients of this other Lohan polynomial. Okay, so with that general result in mind, we can analyze some particular cases where we know how that function decay is, well, not how it is, but the sign, what the sign is. Well, the first one is we start with a sequence of real numbers and assume that the parameter of paraorthogonality is 1, and if that kernel is a Hurwitz polynomial, then the zeros of the paraorthogonal polynomial will have some monotonicity property. They will move clockwise along the left, along the right half of the S1. And we can also obtain similar results for the other half of S1, just changing the initial assumptions. We change the parameter of paraorthogonality and we obtain a similar result. Okay, so now we can also obtain a result for when we have a two-sided polyfrequency sequence. For that case, we have to assume also that n is even and the parameter of paraorthogonality is equal to 1. And again, we can obtain the monotonicity of the zeros. But in this case, we cannot obtain for all the zeros. We can only obtain for the closest pair of zeros to -1. And I'll explain why that happens later. Okay, just some simple example. If we have this function here, and we define this being one of the elements of that sequence, and from that we define the rest of the sequence by this. In this case, when the parameter is equal to 0, we will have the sequence of the moments of the called rotated Roger-Ziegel polynomials. And these polynomials, they have all the coefficients positive, and so when you perturb just a little, when you perturb this element of the sequence just a little, that Toeplitz matrix will remain positive definite. The coefficients of the orthogonal polynomial will also remain positive. And we will have and by using our theorem, we will obtain the monotonicity for the closest zero of the corresponding paraorthogonal polynomial with the parameter of paraorthogonality -1. We'll obtain the monotonicity for the closest zero to -1 in this case. Now, as I said, we could only obtain these results for the closest zero to -1 or 1, and in our case, it's because we are using a result from Barnard and some other authors that states basically the following. You start with a polynomial with positive coefficients, then you remove two zeros, of a pair of zeros. No, sorry. Oh, we start with a polynomial with positive coefficients, then we remove a zero with smallest argument. Then this new polynomial will have all coefficients positive. And we can also do that for the following. So imagine you have a paraorthogonal polynomial with all coefficients positive, and then you remove this zero, the 1. So the polynomial which has all these zeros, all these other zeros, will also have positive coefficients. But if we do that again, then the polynomial with all these zeros will also have positive coefficients. But then we are only interested in removing this pair of zeros, so we would have a polynomial with positive coefficients multiplied by z minus 1. So it's not always easy to see that all the coefficients of this product are positive. So that's one of the reasons why we only have this result for the closest zero to minus 1 or 1. And the restriction on the degree about being even or odd is because when you have a polynomial of degree even, you must have minus 1 and 1 as 0, so you fall in this case. And these are essentially our results. This presentation was based on this first reference, and the other ones are when you vary the weight function, you are working with only the weight function instead of just one of the elements of the sequence, which of course depend on the weight function. And I think that's it. Thank you.
Okay, thank you very much, Alexander. Alexander worked in this proof during more than 2 years and presented this really fast, so I'm very happy to reduce 2 years of work in close 20 minutes. Remark, questions? Okay.
Thank you for the very nice talk. One of the assumptions in one of the earlier theorems was that you have positive definiteness for all t.
Yes.
And now my question is, can you relax it? So, for example, have only positive definiteness for t, let's say, in some interval, or do we really need all t's?
Yes.
Thank you.
When we say for all t here, we are considering, well, it's not for all t's, saying we just want to know what happens in a small interval. So, yes, we are just making a small perturbation there.
Yes, there are small perturbations, but there are assumptions in the theorems that fix these intervals. It's an open interval, of course, but obvious reasons. Yep. Yeah. But the conditions are essentially related with the positive define of the Tepel's matrix, and indeed with the existence of the orthogonal polynomials on the unique circles and the parorthogonal polynomials defined through that polynomials. Okay, more questions and remarks? Okay, if not more questions and remarks, just to say thanks again to Alexander. Alexander, thank you very much.
Thank you.
Okay, our next speaker is Guillermo. Guillermo is also from Coimbra, and Guillermo, well, the presentation of Guillermo is also related with Markov, but a different theorem from Markov. but are really close. Guillermo, we will talk about probably the most beautiful theorem of Markov, which is the theorem of Markov related with the monotonicity of the series of the orthogonal polynomials and its extension. Thank you, Guillermo.
Okay, thank you. Good morning. So I'm going to be speaking about some properties of zeros of orthogonal polynomials. So in principle, one could speak about many properties like the distribution or the asymptotics, or one could interpret the zeros are charges that are in equilibrium with certain potential, but in this case, we're interested in studying the monotonicity of the zeros with respect to certain parameters. So we assume, similarly to previous presentation, that the measure depends on a parameter, and so the zeros of the associated orthogonal polynomial can be interpreted as function of the parameter, and so we ask ourselves how to behave with respect to this parameter. In this regard, it was Markov who first produced three significant results. So in this talk, we are interested about this following result that was proved in 1886. In this case, we assume that well, we got a measure. This measure depends on this parameter, and is absolutely continuous with respect to this other measure, and the parameter falls into this omega. And so the result is very simple in its form, and it states that the zeros of the associated orthogonal polynomials are increasing function of the parameter, provided that this function here is increasing function of x on the real interval the measure is supported. So here simply this quantity is very straightforward to compute, right? It's simply derivative with respect to the parameter, and it gives us the monotonicity of the zeros. And we also got the second part, whenever this quantity is decreasing, then the zeros are decreasing function. So we may make use of this result to obtain the monotonicity of the zeros of certain family of orthogonal polynomials. In particular, here we have the Jacobi polynomial, right? This is the usual measure, and here we got two parameters, alpha and beta. And well, we compute these quantities, and we obtain that this function is decreasing with respect to x, and this is increasing, and so we obtain that the zeros of this polynomial decrease with alpha and increasing with beta. This is another example. This is the Ham polynomial. They also depend on two parameters, alpha and beta, and similarly we obtain that the zero decrease with alpha and the zeros increase with beta. So the beauty of the result is simplicity, right? The philosophy is that the measures are simple, and so the monotonicity of the zeros should also be obtained in a simple way. Because as a matter of fact, one could have made use of the explicit expression of the orthogonal polynomials to derive the monotonicity of the zeros with respect to these parameters. But the computation are unnecessarily cumbersome and complicated when it all falls on the measure. Also notice that in this case, the measure with respect to the absolute continuity we have is continuous. In this case, it would be like Lebesgue measure. I mean this mu, and in this case, for the half polynomial is discrete. So the original proof by Markov only considered like the Riemann case, and later on it was extended by Sego to consider any particular any arbitrary measure. And well, this proof was given, I believe, or at least it's in the book in the volume that was published in 1939, and it relies this proof of this extension of the original Markov theorem. It relies heavily on this property that we call Gaussian quadrature. Like we got a measure, right, and we want to approximate the integral of this measure. In order to do so, we consider well, we want to make it valid for a certain degree of up to a certain degree of a polynomial, right? And so we In order to achieve this, we fix a polynomial. We consider it zeros, and these zeros will work as the nodes of the quadrature. And then we have some associated weight that are strictly positive, and this is relevant. And so it holds this formula that is valid for any p, for any polynomial of degree at most 2n minus 1. And here we see that we are evaluating the p on the zeros of the orthogonal polynomial. So the important part of this result is this is as good as it can get, this quadrature, because for example, if we were to consider polynomial, if we were to assume that this is true also for polynomial of degree 2n, then we could put here pn squared. So pn squared would have a positive integral. This would be strictly positive. But here we would be evaluating pn squared on its zero, so it should be zero. So this is as good as it gets. And the thing is that this proof relies heavily on this two nice property, that is that this weights, these lambdas are positive, and this is true up to a maximum degree. But the issue with this, though it's an elegant result, is that when we are trying to extend this result of Markov to other classes of orthogonal polynomials, and we try to mimic the procedure in this proof, it happens that the quadrature formula that are associated to the rest of the classes of orthogonal polynomial are not as good as this one. So, for example, we wouldn't have this positivity of the weight, or we wouldn't have that this result is valid to this degree. So, for this reason, it happened that this extension of Markov theorem on the variation of zero was stopped. There weren't any kind of extension due to this inability. So, in order to produce an extension, the first step, was taken by Kenya, our dear Kenya, and he got rid of the quadrature and decided to try to obtain the similar result, the same expression, but in a simpler way, setting aside the quadrature and finding a simpler argument that depended solely on the fundamental properties of the polynomial, mainly on the mean definition, so that we are able to extrapolate them to the rest of the class of polynomial. And in particular, in 2019, he proved this extension of the Markov theorem in the real line to the class of paratogonal orthogonal polynomials on the unit circle. So in this case, we got a measure that is supported on the unit circle, right? And the unit circle parameterized by this theta. And well, in this case, as Alexandre told, the paratogonal polynomial, they lie on the unit circle. So the monotonicity in this case is not that they increase or decrease, it's that they move counterclockwise or clockwise, depending on, again, this quantity, which is the same as in the original Markov theorem, the real line, is increasing or decreasing respectively. So in this way, we obtain that the Markov theorem remain essentially valid in this context. And well, okay, the idea of the proof is kind of straightforward, and it relies on this simplicity of the zeros of the associated orthogonal polynomial, and well, on expressing this the monotonicity, the variation of the zeros in this form, and operating. Okay, but the proof itself is pretty technical. So if you are interested, you may check the paper itself. But the important part is that this procedure can be replicated up to a point, and we may extrapolate the ideas to extend the result to the class of multi-orthogonal polynomials in the real life. So now I'll speak a little about the multiple orthogonal polynomials on the real line. I'll talk about the definition, then some particular results about some families, about the monotonicity of zeros of some families of multiple orthogonal polynomials. And then I'll show how, with these ideas, we can obtain another extension of Markov zero to this class of polynomials that, well, up to a point, more or less extends the results that were obtained in a particular way. So, well, this multiple orthogonal polynomial on the real line, they're also called Hermite-Padé polynomials because they appear in Hermite-Padé approximation, right? Well, they're relevant in number theory, and the information of the zeros is important. But the issue was that the results of the zeros were scarce, and they were very particularized to the families of polynomial considered. Well, and in particular, well, it was this problem of extending the Markov zero was stated by Ismail. Okay, and so the definition is as follows. In this case, we got we don't have only one measure. We had m measures in general supported on the real line, and well, in principle, you don't need to be absolutely continuous or anything like that. But for the purpose of this talk, we assume that it's absolutely continuous with respect to this weight function. And now, instead of fixing index, we fix a partition. Each of these number here is associated to each of the measure, and they all sum the degree of the polynomial that we will consider. And so, a polynomial of degree n, this degree, is said to be a multiple orthogonal polynomial on the real line with respect to this measure and this partition if it satisfies these series of conditions that depend on this k, right, which is associated to the measures, and simply states that the orthogonality in this case is distributed within amongst the different measures. And so we see that it's orthogonal, so to say, up to degree nk minus 1 if nk is the index associated to the measure k. Okay, so in general, this polynomial may not exist. It depends on the measure and on the relation of the sets of measure that we are considering. And well, this is some notation. We say if this polynomial exists, then the partition is said to be normal. And if we fix a set of measure, and for a partition we get the existence of the polynomial, we say that the set of measure form a perfect set. Well, in particular, there's this condition here that ensures that a partition is normal and is related to this weight, these weights that that construct the measures. And well, it's related to this so-called algebraic Chebyshev system, and we say that this system, or an arbitrary system of n function, is algebraic Chebyshev if in an arbitrary linear combination of the function has at most n minus 1 zeros, but the definition itself is not relevant. The idea is that if we got that this set of function satisfy this AT property, then the partition is normal. And interestingly, there exist some classes of sets of measure for which every partition satisfies this AT property, and so they are perfect, and they are the interesting classes of sets of measure that are studied in this context. So in this case, the more studied flavor of set of measure are the Angelesco and the Nikishin. So in the case of the Angelesco set of measure, it's happened that all the measure has disjoint support, and in the case of the Nikishin set, it's quite the opposite. Of all the supports coincide and they are related by some transform, but I'm not going to go into much detail about Nikishin sets of measure, and we will focus mainly on the Angelesco type multiple orthogonal polynomial and the extension to Markov to this kind of context. So as I was saying, we got a set of measure, and then their supports are pairwise disjoint, real interval, of course, and these are some properties. So we said that every partition was normal, okay? And also this is important for the proofs, as I stated before. We got that the the n zeros of the multiple orthogonal polynomial are simple, and also it happens that if nk is the index associated to the measure k, there are nk zeros located on ik if ik is the support of the k measure. And so we may we are able to decompose the multiple orthogonal polynomial in this way, and this gives us some certain properties of this Q, and in particular we obtain that this Q cannot behave like an orthogonal polynomial with respect to its associated measure, but modified through the rest of the Q's, which are which hold the zeros in the other intervals. And well, these properties are relevant for the proof itself of the Markov extension, but we won't go into much detail. And this is the simultaneous Gaussian quadrature that I was talking at the beginning. So in this case, we also have like a similar formula that is valid for every measure. Here, the measure are in this L, and we got weight for each L. So it's simultaneous quadrature because the nodes are the same, but the weights, of course, change for each measure. But it has two main issues, as I was saying at the beginning, and that's the reason that these quadrature are weak, is that it does not go up to the maximum degree. So it goes only to n plus nl, if nl is the index associated to the L measure, -1. In the other case, we got n plus n minus 1. And also, it happens that the weights in this case are only positive if they belong to the support, to the interval, if they're associated to the nodes that belong to the interval where the measure is supported. And the rest of the weights are alternating in sign, so that's why the classical arguments by Sego were not able to be replicated in this case. And now speak about some families of multiple orthogonal polynomial and some particular results about their monotonicity. So here we fix two measures, and here we consider the Jacobian-Jelsko polynomials that results when considering these two measures that are defined from a to 0, and this a is negative, and from 0 to 1. And of course, it constitutes a generalization of the Jacobi polynomial. So in principle, at the beginning, there exists an explicit formula for the Jacobian-Jelsko polynomial, of course, and it was introduced in this way as a generalization of the Jacobi polynomials. But later it was found out that it corresponded to this multiple orthogonal polynomial with respect to these measures. And only recently, some particular results about the monotonicity of the zeros of this polynomial were obtained. This author, in particular, obtained only monotonicity of the zeros, but for the so-called diagonal case, when n1 equal n2, and in particular, of course, n1 could be different than n2, and in particular, he obtained that the zeros increase with this alpha, which lies at the left boundary of the leftmost measure, decrease with this gamma that is on the right, and also with this beta, which is in the middle. It happens that the zeros on this interval decrease, and the zeros of this interval increase with respect to beta, whenever the case is, whenever a equal -1, so we are in the symmetric case. And later on, recently this year, this author improved a little this result and obtained the same result, but for the non-symmetric case, but still only on the diagonal case. So for this result, they employed the explicit formula, but in this case, we are dealing with multiple orthogonal polynomials, and we got different measures. The explicit formula itself, it's more complicated, so we are not able to obtain the same results as in the case of the classical Jacobi polynomial, where the expression were simpler, and so the computation were simpler, were simpler. So here they are only able to obtain properties in the more symmetric way when n1 equals n2. And well, also there exists another two families of multiple orthogonal polynomial that generalize the Laguerre polynomial and the Hermite polynomials, and they are related also to the Jacobi-Laguerre polynomial that I introduced before by asymptotic relation. So the monotonicity of the zeros of the Jacobi-Laguerre polynomial are related to this one. So one obtains the monotonicity of the zero with respect to the other. So in order to try to extend these particular results, not only to these families, to arbitrary families, we can proceed in a similar way that in the case of the parsogonal polynomials on the unit circle, and we obtain this Markov extension to Angelesco type multiple orthogonal polynomials on the real line. So in this case, consider a measure as I was speaking about, and well, of course we got the parameter again in the weight, and this time we obtain a slightly worse result than in the case of the parsogonal polynomials on the unit circle, because well, apart from this usual condition that one imposed on the measure for the monotonicity, one also needs to impose this condition that is kind of like this one, but instead of derivating with respect to the parameter, we derivate with respect to x, and we need to impose that it is decreasing so that everything falls, and we may reobtain the Markov theorem. So that's why I call it a partial extension. But despite this inconvenience, we are able to improve a little the results of this particular family. In this case, of course, we obtain very simply the derivative, and we see that this function increases with respect to x, this is decreasing with respect to x, and this also is increasing with respect to x, is alpha is negative, so we obtain the usual condition that Markov assumes. And of course, maybe I didn't explicitly talk about this, we're imposing the classical Markov condition in each measure, because in this case we got different measures. But the problem here, though this is straightforward, is that if we want to compute this, the fact that this derivative with respect to x is decreasing, there exists some restriction of the parameters. So in principle, the polynomial are defined with these parameters greater than -1, but in order for this quantity to be decreasing with respect to x, and so the result to be valid, we need to impose this, and so we obtain a partial improvement of the other results, because in the other result we only it was only considered the diagonal case. In this case, we obtained the fact that the zeros increase with respect to alpha, decrease with respect to gamma, and increase with the left endpoint A, but only when this restriction of the parameters are considered. Despite this, I believe that this condition maybe can be taken out, and so we could be able to obtain an adequate, more real Markov extension to this type of polynomials. And that is all I wanted to speak about. Thank you.
Thank you so much, Guillermo. Questions and remarks?
Yes, thank you for the nice talk. I have a question regarding the proof of your theorem. Which method do you use? Do you go through the Gaussian formulas, or do you use this approach of Kenya? Or, yeah, just
yes,
small comment. Yeah, thank you.
Yeah, no, the issue was that, let me go back to, the issue was that in this case, what I wanted to show here is that if we compare it with the Gaussian quadrature, it's weaker, because here we got that some weights are positive, but they are alternating in sign, and also we don't have that it's true for 2n plus 2n minus 1, as in the classical case. And these two properties, the fact that the weights were all positive, and that the fact that the formula is valid up to the maximum degree were crucial for the proof that provided SEGO. So in this case, we are not able to replicate those arguments, and so for this particular case, we go with the more elemental procedure that was based on the result that Kenny obtained for the partial polynomials. That was the idea.
Thank you. More questions or remarks? If no more questions and remarks, so let me just say it's a remark. Yes, and that condition that appears are related with the fact that a certain matrix is a Z matrix, and these results is a partial results because it's not submitted and not published, and we only will send the results which prove that indeed, also in this case, Markov's theorem remains valid. If you not, there are many good papers and recent papers just for very particular case of two measures, and in a very particular case, that is the symmetric case. If you have Markov theorems, all this is solved, and we solve also, well, the problem was collected by Ismail, but it's a very well-established problem to extend Markov theorem to multiple orthogonal polynomials and using number theorem and so on. If not more questions, thanks again, Guillermo. Guillermo is starting, well, he will start his PhD next year, okay? So he is presenting our first word, which is a partial results for a partial student. Okay, thank you so much. Okay, and now it's time to the last talk of this Congress. For that, we have very special persons, very close to Petronil, which is Susana Moura from the University of Coimbra. Thank you so much, Susana.
Thank you, the organizers, for the opportunity to give a talk in this conference, and special to Kenya for the kind invitation. This is also special because it's in memory of a dear and missed colleague in Coimbra, so Zé Carlos. So I will talk about some tool that can be used to characterize how unbounded are the functions in some function space. So this concept of growth envelope. Then I will apply to this concept to Morris spaces and generalized Morris spaces. And if time permits, I will also speak a little bit about smoothness Morris spaces. Okay, before giving the definition of this growth envelope, I need to recall some concepts well known. So if we have a function, a measurable function defined in Rn, let us say, scalar function. So the distribution function is defined for any sigma greater or equal than 0 as the measure, the Bechdel measure of the set of points where the f in its modulus is bigger than sigma. Based on the distribution function, one can define the decreasing rearrangement of f as the infimum of all sigma, such that the distribution function on sigma is less or equal than t for the given t. So these two functions, they are decreasing in the right continuous, and the important fact is that the f and the f star, they are equimeasurable, and just in the particular case where the distribution function is continuous and strictly decreasing, this f star is just the inverse of the distribution function. And if some f is a step function, then what the decreasing rearrangement is just that the blocks are ordered so that we have a decreasing function. In general, the two functions are generalized inverse of each other. So the definition of the growth envelope was, let us say, invented by Dorothea Rosk and Strebel in 2001. And so it's some way of trying to measure how unbounded can be the functions belonging to some function space. So assume that X is some quasi-Banach function space, this, let's say, in Rn, because this can be defined also in some measure space. So the growth envelope function of this X is a function defined on the positive real line with values that can be infinite, and is defined in the following way. So we pick some positive t, and we look at the rearrangement at t of any function in the unit ball in X. So, and it's the supremum, it will be the value of the growth envelope function at t. So we have always a decreasing function. The growth envelope function is always a decreasing function, and its value at 0, that can be infinity, is the limit of this decreasing function as theta goes to 0. So it is clear then that this function will be bounded if and only if we have an embedding of x in L infinity. So the interesting is when it's not embedded in L infinity, how this function behaves. And so they also included an additional index. So suppose we have some quasi-Banach function space. We have this growth envelope function. I should say that we always work with equivalent quasi-norms in a space, and this gives us equivalent growth envelope function. So to be precise, we are working in a class of functions. And so we pick some representative and assume we have a space that is not embedded in L infinity. We define such a function. Suppose that this will well behaved if this function, for instance, is a continuous differentiable. And we define the Borel measure associated with the function. And then from this definition, it's immediately that this inequality here holds with V infinity. So taking this the supremum O over T. It happens that the left-hand side is decreasing in V. So, and we look for the infimum of all V's such that this inequality is fulfilled for any function in X. So in almost examples, this infimum is even a minimum. So we end with a pair, a function and some index that is called the growth envelope function of the function space X. So this concept was applied quite a lot of examples, and gives good results. I start with just some properties. Of course, when the space is embedded in L infinity, this happens if and only if the growth envelope function is bounded. And when embedding, the growth envelope functions satisfies this inequality. And once we have an embedding and the growth envelope functions are equivalent, this equivalence is always in the sense that the quotient is bounded from below and from above by positive constants, then the index satisfies this inequality. Okay, just a very first example. So Lorentz spaces are defined for P and Q positive numbers. Q may be infinity, as the collections of the measurable functions f such that this quantity is finite. This is the Lorentz space LPQ. And these, of course, recover the Lebesgue spaces once the P equals Q, and the growth envelope for this space is this pair. So the P appears in the growth envelope function, okay, and the Q appears as the additional index. Well, recently we were working in Morris spaces. That is another class that extends the Lebesgue spaces. I present you the definition. So this, let us call the classical Morris space. MUP is defined where P is less or equal than U. Otherwise, this space will be trivial. So it's the Morris space MUP. So it's the collection of the functions that are P locally integrable and such that this quantity is finite. So we have here some mean. So the BXR means the ball centered at X with radius R. Okay, and this is the Lebesgue measure of the ball. Of course, this sorry, this should be a capital R, sorry. So we have this mean, and there is some weight, depends on U, okay? So in fact, these measures do not depend on the X, but is like this just because I will be generalizing this in a while, okay? So these spaces generalize the Lebesgue spaces. When U equals P, this defines nothing more than the Lebesgue space LU, okay? So they also generalize the Lebesgue spaces. But if here P1 is strictly less than U, then we have a strict inclusion. And this class of functions fix the U, they are the smallest the P, the biggest the space is, okay? And we were interested in how unbounded can be the functions in these function spaces. Measure in terms of the growth envelope. Do you have the same as LP? So this is just an example that this is the conclusion, but I will skip it. Just on property, let us go to the growth envelope function. So the growth envelope function of the Lebesgue space, we have seen LP was T to the power minus 1 over P. So when we have U, this is the result. And as I've shown you in the last slide, we have an embedding of the Lebesgue space in the Morris space. And so by the properties of the growth envelope functions, we immediately have a lower bound for the growth envelope function of the classical Morris space from below. And we were quite surprising when we realized that when P is strictly less than U, so when we have a proper Morris space, it turns out that the growth envelope function is infinity for any T. So the functions in this function space can be, let us say, admit much more unboundedness than the Lebesgue spaces. Okay, so we were a little bit surprised at that time, and on the other way, with our research in the recent years, we come to consider some generalized Morris spaces. And the question was, what is the point? Why we come for unboundedness of the growth envelope function? How does it depend on some parameter that comes in these more general Morris spaces? So as you can see here, if you remind the definition of the classical Morris spaces, is that now this weight that was here in front of this mean is now a function of the r, so the radius of the ball, that can be more general than in the previous definition. Okay, so this definition goes back to Mizuara and Nakai, and in the definition, this function can be any function, just not trivial zero. Okay, so of course we recovered the classical Morris spaces with this weight function. Of course, the Lebesgue also in. When this function is 1, we have the L infinity, and we can also consider other examples interesting with different functions phi. In practice, one requires this function phi to belong to some class GP. So the P is here, and so in the definition, this phi can be any function of this type, non-trivial, and we usually require this condition. What this means? This means that the function is increasing itself, and when multiplied by t to the power minus d over p, it turns out to be decreasing. This is the definition of this class GP. So we can have examples in this class, not just the power, t to the power d over u, as in the classical Morris spaces. We can have different behavior locally in another behavior for big T, and we can also have some logs in, okay? And there is no loss of generality by requiring the function phi to be in this class GP. That is a class that also becomes bigger as smaller the p's are. And this is due to this lemma. So the Morris space is non-trivial if and only if this condition is fulfilled. And once this condition is fulfilled, it's also possible to find a function in GP so that the spaces coincide in the sense of equivalent quasi-norm. So there is no loss of generality in assuming from beginning that the function is this in this class. So what we know is that the growth envelope function of LP was this function. The classical Morris space, if P is less than U, so the proper Morris space was infinity. And what is the rule here of phi here? And it was quite interesting that we find out that this phi is some kind of bridge between the Lebesgue and the proper Morris spaces in the following sense. So we have just 3 possible cases. For this space, either the growth envelope function is a bounded function, and this depends on the limit of this increasing function at 0, and this corresponds to the embedding in L infinity. If the space is not embedded in L infinity, what happens? So now we consider that the limit is 0, of course, not to be embedded in an infinity. And then depending on the limit of this decreasing function at infinity, either is positive or is 0, we are in the situation of the proper Morris spaces or the Lebesgue spaces. So we were quite surprised with the result at the end. So this phi, regarding how unbounded the functions are, does not give any new case. So just the boundedness, Lebesgue space, or proper Morris space. Okay. Then afterwards, we were thinking about what happens in smoothness spaces based on these spaces. So since I'm not, don't know if you are familiar with this kind of function spaces, I give a brief overview about them. So the starting point are the classical smoothness spaces. By classical smoothness spaces in this setting, I mean Bezoff or trivial-Zorking spaces. So these spaces can be defined by Fourier analytical tools. So if we have some smooth dyadic resolution at unity, any temperate distribution can be represented in this way. So here this stands for the Fourier transform, and here for the inverse Fourier transform. So any temperate distribution can be represented with these building blocks that in fact they are can be taken pointwise. Okay, and so since all function spaces here will be defined in RD, as before, I will omit the RD from the definition, and so these classical spaces are defined the following way. We have some S, real number, PQ, positive numbers that can be infinity, at least for the Bezoff space. And so this Bezoff space, BSPQ, is the set of the temporal distributions such that this quantity is finite. So what do we have here? These are a sequence of functions, and we have this weight here dependent on S. S always stands for the smoothness parameter. Okay, so we take first the LP norm and then the little LQ sequence norm or quasi-norm. If this is finite, we have a distribution in this Bezoff space BSPQ. If we change the order, and here we need that P is less than infinity, then we define the trivially Zorking space FSPQ. These are two scales of function spaces very well studied that covers important special cases as Sobolev spaces in the F scale, Lebesgue spaces, Sobolev spaces, Bezoff potential spaces, classical Bezoff spaces defined by difference, and so on. So many tools available. The spaces can be defined even using other tools like wavelet, atomic atoms, and so on. So here the S stands for smoothness, P for some integrability, and Q for some refined integrability. And along the years, there have been quite a lot of generalizations in the setting of these spaces, either by generalizing LP by some rearrangement invariant function space, generalizing the smoothness by some generalized smoothness, even with variable exponents. Then we are more interested now replacing the LP by Morris spaces, or in particular now by generalizing Morris spaces. So the definition then looks like this. So we have just replaced the LP by the generalized Morris space, or it could be the classical Morris spaces. Okay, just the notation changes a little bit. I don't know the reason. It's not established that we use the N for the Bezoff Morris spaces and the E for trivially Zorking spaces. And so, of course, examples. We have the classical Basel-Morey spaces, triple-Lizorking spaces, and we have this weight. Of course, when the U equals P, we have the classical Basel and triple-Lizorking spaces. And what about growth envelope functions? Since we are dealing now with distributions, the growth envelope just makes sense or is reasonable to take if we are living in the world of the temporary distributions, of course, because we need to work with functions. And interesting if the space is not embedded in infinity, otherwise the growth envelope function is just a bounded function, okay? In the following, it's quite standard if we want to denote both classes, which use the letter A to write it in some more compact way. And for this classical basic Lizorking space, so we have to live in the world of regular distributions and distribution that spaces that are not embedded in infinity. And for these spaces, everything is well known, okay? So just to recall that if we write this nice diagram where we put integrability over against the smoothness, so the Q is not in here because it not plays a so important role just in limiting situations. So above this orange line, let us say above this line, we are living in the world of the regular distributions. This is the case of what interests most. In this case, we have some situation where we can deal with. Similar for the triple Lizorking space. As for the embedding in L infinity, we are embedding in L infinity if we are above this critical line. S equals, sorry, should be D over P. I forgot to change. Okay, this N is for the dimension of Rn. Sometimes I'm using the D, sorry. Okay, so for growth envelope functions, growth envelope, we are interested in this strip over here. So, and the results are well known. Just to show you that now in the growth envelope function, what appears is the P, the smoothness, S, the dimension here. So it's for the growth envelope function, and for the index, it appears the Q in the index. So some sense this can be seen as also some embedding of the base of space in some Lorentz-Zygmund space in Lorentz space. And in the critical line, then some log term appears, okay? So this is the result for the triple Lizorking spaces, so it's just well known. Then the first case we considered was to replace the LP by the classical Morey space. And we have studied this some years ago. And when P is less than U, so the proper Morey space, whenever we are living in the world of the regular distributions and the space is not embedded in infinity, it also turns out that the growth envelope function is an infinity. Okay? And now we were concerned again, what about considering some generalized Morey space? Okay? And I just recall you that for technical reasons, or to be more clear in the presentation, we assume that besides the function phi belongs to this class GP, we assume the phi takes the value 1 at 1. Of course, this is not important because we can also have an equivalent norm if this is not the case. Okay, and please note that since by definition this function over there is decreasing, in this is increasing, and the value of the function at 1 is 1, so the limit of this function at 0 is some number between 0 and 1, and the limit as this is decreasing is a number between 0 and 1. And we have studied the conditions for the embedding Allen lock different cases, but I will not present you here. Up to a certain point, we have necessary and sufficient conditions. That's one case is not clear for us, and we're able to prove the following. So, for the Bezov space based on the generalized Morris space. So the growth envelope function is bounded, so we have inclusion in L infinity if and only if this conditional holds. And in the case we have no embedding in L infinity, we can look at the limit of this function at infinity. If this limit is 0, then the growth envelope function is infinity for all t. In case this is positive, because this can be, we have seen either 0 or either a positive number less than 1. So in the remaining case, if the limit of this function at 0, this is now something that appears in the smoothness spaces. It does not appear this condition for just for the Morey. If this is finite, then we have what is stated here is just the behavior as in the classical Bezov space BSBQ, so nothing new. I have not written here, so what the case that is remaining is when this is positive and here is 0. And the situation now is not somehow perfect. We have some conditions, so the phi now plays a role, but we have to write a condition about the behavior of phi near 0. And the result is not so nice, so we are still working on it. And up to now, we also have not dealt with the case of the triple spaces. So this is somehow ongoing work with my colleagues Dorothy Rosk von Miena and Leszek Richard from Poland. And this is some reference, and thank you very much for your attention.
Thank you very much, Susanna, for this nice talk. Okay, time to questions or remarks.
So in the beginning, you started with a quasi-Banach function space, and you say that if the space does not embed into capital infinity. So first, so this embedding is in what sense? What kind of embedding?
The embedding of x in L infinity?
Yeah, what kind of embedding? Is it a linear isomorphism or continuous embedding?
Just the functions in x are bounded almost everywhere, and that the norm is bounded by in L infinity, bounded by a constant phi norm in x.
So you are saying continuous embedding, right? Then you are talking about continuous embedding. It's not linear isomorphism. It's not.
No.
And then that condition, how to verify? For example, you have a set of functions or space of functions. How can you tell whether it does not embed into capital L infinity? Because that assumption.
Well, we have to have now in these spaces we have a distribution. So we have to assure that we are we can identify with functions. But in general, if you have just a space of functions like Lorentz space or even the Morris spaces, we have to calculate the things. I don't know if I understood your question. In the examples, most examples we are using atomic decompositions to deal with, to construct functions that satisfies our extremal functions in some sense. I don't know if this was the question, sorry.
Yes, so can you go to the first slide? Go to your first slide. Yeah, I see the X. Go.
Here or here?
No, continue. There's somewhere you assume X. Yeah, you assume X does not.
Just
X does not embed into capital infinity. I think that's. Here.
Yes, because otherwise this function is bounded. The bounded function, and the interest is to measure, to study better the case where the functions are not bounded. How unbounded can it be? Let us say.
Okay, so that condition you just check case by case. Is that what you're saying?
Yes. If we are in such a case, we try to have a better information about the space. Okay, so we built the function. Assume the function, this growth envelope function, is not a bounded function. Since it is decreasing, it tends to infinity as t goes to 0.
Okay, let me make my question another way. So is there any like a criteria for X not embedded into capital infinity? Is there any like a condition you have? So if X satisfies condition, some condition, then X does not embed into infinity.
This condition is studied case by case. Yes.
Case by case?
Yes.
Okay.
Yes.
There's
Case
no
by
uniform.
case.
Okay.
Yes.
All right.
Yes.
Okay.
For instance, let me see. For the classical spaces. Okay, these are the conditions, for instance, in the parameters. These are the well-established conditions. We know exactly when we have the embedding L infinity. And so, for the growth envelope, we avoid these cases. We study in the other remaining cases. Okay?
Okay, thank you.
More questions or remarks? Any other question or remarks? If not questions and not more remarks, thanks again, Susana.
Thank you.
And with this last talk and between us, let me say thank you to everybody. I feel Petronilo close to me during all this week. He will be very happy to see what we did. With that, I'm officially close this conference. Thank you to everybody again.
Audio Jungle. Audio Jungle. Audio Jungle. Audio Jungle. Audio Jungle. Audio Jungle.